point spec. One sort of thing that a lot of people like to do is have JavaScript talks or write JavaScript articles where it's like, hey, check out this part of JavaScript where it's kind of goofy and weird and doesn't make sense. Let's laugh at JavaScript and hate on it. But instead, I'm going to try to point out some things that are weird and goofy about JavaScript and then explain how you can understand them and why it ended up that way, and then maybe laugh at it just a little bit, but mostly try to convey some understanding about how things are. So with that, here is NaN. So to start, NaN stands for not a number. You've probably seen it somewhere before, but let's delineate exactly what will give us NaN and how we might run into it. So the first case is if we go and do some fuzzy math. So if you ever try to divide by 0, or if you do things with infinity that are just not how infinity works, you're going to end up with NaN. The next category is complex numbers. So if you try to do anything where you would end up with a complex number, there are lots of different ways. If you remember trigonometry or math or any of that, you can come up with more than just what I've shown here. But in general, anything that would give you a complex number is instead going to give you NaN. And the third category is taking something that is obviously non-numeric and trying to turn it into a number when there's not really a reasonable way to do that. So it turns out in JavaScript, a lot of things that you might think can't be turned into numbers can be turned into numbers, but a lot of things can't. So if we try to use parseInt or parseFloat or the number constructor or the plus unary operator, which is the same thing as the number constructor basically, on things that don't turn into numbers very well, then we get NaN. So we know where we can run into NaN or where it appears, but what really is it? How does it behave? So not a number is just a particular JavaScript value, kind of like undefined or null, a very particular JavaScript value. And it turns out that not a number is actually a number. So we're starting on the train of goofy things a little bit. But it also turns out that not a number is not a number also. So at least if we apply the double negative, it does make sense because it is both a number and not a number. But it turns out that that makes things kind of tricky to test because if we try to use an assertion library to check if two things are equal, and we check for NaN equaling NaN, we get an assertion error. So we have to figure out NaN actually stands for not a NaN. And that actually kind of comes from Arya back there, who's giving a talk later this evening with his little tweet that's your annual reminder that NaN actually is this lovely recursive initialism that stands for not a NaN. So we know where it comes from, we know kind of something about it, but how do we actually tell if something is NaN if we can't just use equality? Well, easy, we just use the isNaN function, and that's going to solve all of our problems for us. But it turns out that isNaN also returns true if you give it things from that third category where you can't turn it into a number and it's not already a number. So if we give it a string or an array that's not empty or an object, it's also going to return true. And we would like to have a function that only returns true when we give it the specific NaN value. That way, you know, we're not running around thinking that things are NaN when they're actually just not something that can be turned into a number. So what we can do is we can write our own. So if we just check that the type of our value is number and that it passes this isNaN function, then we get what we want. We return true only for NaN and we return false for all of these other things. But we can also remember what we just learned, which is that NaN means not a NaN, and we can actually just check for x not equaling x. And that actually does the same thing and works how we want it to. And that works because NaN is the only value in JavaScript for which the equality operators are non-reflexive. So if you ever see the pattern x does not equal x, you know that that's really a check for x being NaN. If you don't like that pattern, there is an ESLint rule that can tell you not to use it. But I love that pattern, so make of that what you will. But now that it's ES 2015 and ES 2015 has shown up to save the day and solve all of our problems with JavaScript, it has solved this problem for us as well, and we now have number.isNaN, which also behaves exactly the same way as those other two ways to check if something is the NaN value. And we also now have object.is in ES 2015, which uses the internal same value comparison operator, which correctly identifies two things being NaN as being NaN and does not give you any other false positives. That's also kind of the same reason why if you have a set data structure and you try to add NaN to it multiple times, you don't run into this problem of having like 100 NaNs in your set. You only get one NaN in your set because inserting things into sets also uses this same value internal operator, sort of, kind of. So anyway, enough about NaN and JavaScript. NaN is not just a JavaScript thing. So let's talk about what the IEEE 754 floating point spec has to say about NaN, because that's where NaN actually gets defined. So the fortunate thing is that most programming languages implement their floating point stuff and have their NaN behavior all according to the spec from IEEE. So if you do understand NaN in one language, you probably understand it in most others as well. But the keyword there is most. So a little bit of a fun fact about that. So there's one piece of the IEEE spec, namely the POW function for exponentiation. So it defines POW of x, y is x to the y, so 2, 3 gives you 8. And there are a few cases where POW gives you NaN. So namely, if your base is negative and your exponent is not an integer, then you get NaN. Or if either your base or your exponent is NaN, then you get NaN. And so there are a few cases where POW will return NaN. And that's written in the spec, and all languages do that. There are also 3 indeterminate forms for POW, namely 0 to the 0, infinity to the 0, and 1 to the infinity. There are alternative power functions that will return NaN for all of these, but the base standard POW function that's been around forever is defined to return 1 for all of these. That was originated back in C, was standardized in C99 and the POSIX spec, and most languages have kind of fallen into line since then and inherited that behavior. So here's what Python does. It gives you 1 for all of those. Here's what Ruby does. It gives you 1 for all of those. Here's what Lua does. It gives you 1 for all of those. All 3 of these languages, of course, have floating point spec in common. But what about JavaScript? So 0 to the 0 is 1. Infinity to the 0 is 1. But what about 1 to the infinity? Does everyone have a guess what math.pow of 1 comma infinity in JavaScript will return? It's NaN. Why? Why? Why is JavaScript the odd penguin out in this situation? Well, a little bit of a history lesson. So this goes back to the spec written way back in 1997. So ES1. Now we're at ES6, way back at ES1, back in 1997. Now this document is actually ES3, but ES3 and ES1 are identical in this section, and I couldn't find the ES1 doc. So here we go. Namely, we're looking at the POW definition, and the important part is these last 2 bullets down here, which says if, oh, you can't see the very bottom bullet, but this bullet conveys most of the point. So if the absolute value of x is 1 and the exponent is infinity, positive infinity, the result is NaN, and the second bullet just says the same thing for negative infinity. So that's just written in the spec, that case should return NaN. That now lives on in the latest ES 2016 spec with the exponentiation operator. It also has these 2 bullets, and now math.pow is defined in terms of the exponentiation operator, so this behavior lives on today in the most recent JavaScript. Timeline of how that came to be. Well, ES1 was specified in 1997. ES6 now 2015, ES7 2016, ES2016, however you want to refer to the modern version of JavaScript. But C and POSIX came along in 1999 and 2001 with their specifications of how it should behave. The IEEE spec, though, did not explicitly specify those cases until the 2008 edition. And so if you look at the spec today, there's this footnote under the definition of math.pow, or I guess the exponentiation operator, which says this was defined in the first version of ECMAScript, and then IEEE 2008 came along and specified there should be 1. We have preserved that behavior for compatibility reasons. So just like the answer to all of the other questions of the forum, why is JavaScript like that? The answer is backwards compatibility. So now that we've established that JavaScript only mostly cares about IEEE 754, what does IEEE 754 have to say about how we actually represent NaN at the bit level? So a float 32 value is 32 bits, and we interpret that in a certain way to come up with some sort of number. We have a 1-bit sign component, and then we have 8 bits of exponent that's offset by 127 so that we can have negative exponents, so that we can have small numbers. And then we have a 23-bit significand, which is basically sort of like our actual magnitude of our thing. it also has an implicit leading 1 point, and then it's just a big binary number. So, example of how we can actually run that through. So then we just like multiply everything together, and we get a number. So here we have -1 to the 0 is 1, so our sign is positive. And then we have this big number, minus 127. That number is actually just 128, so that's 1. 2 to the 1 is 2. And then we have 1.01 in binary is 1.25. And so these bits right here are the IEEE spec float 32 value for 2.5. So what about other values that are represented in certain ways by the IEEE spec? Well, if we have all 1s in our exponent and we have all 0s in our significand, then we have an infinity value, and it's plus or minus infinity based on whether the sign bit is flipped or not. And then our other special value, of course, is NaN, and NaN is any value that has all 1s in the exponent and then any sort of non-zero significand. So what that means is that all of these things are also NaN. So we have quiet NaNs, we have signaling NaNs, we have positive NaNs and negative NaNs, and we can sort of start counting them if we really like, and we can wonder how many NaNs are there? Well, for a float 32, we have 24 bits minus the 2 infinity values, so we have 16,777,214 different NaNs, and that's just for a float 32. But what about a double 64? All of the languages actually use generally double 64s. JavaScript uses a double 64 for all of its numbers. So with a double 64, instead of 24 bits, we have 52 bits. And so we have 2 to the 52 minus 2 is this giant number. And that number is 4.5 times 10 to the 15, which is 4.5 quadrillion. If we turn that into bytes, that's about 10,000 years worth of music. So there are a lot of different NaNs out there. And so if there are so many different NaNs, then it only seems reasonable that if we pick any 2 random NaNs, it's unlikely that those 2 NaNs will be the exact same one, and thus NaN does not equal NaN with probability 1 out of 4.5 quadrillion. Thank you. The slides will be posted on my Twitter and GitHub and stuff. I'm at Lewis Ellis.
Wow, I think that's probably the one talk so far where I think it would have been appropriate to drop the mic. But at first I was like really confused because I'm like, what did JavaScript numbers have to do with my grandma? Like, you know, and then when you started getting to the end, it got really existential, like, you know, existential, thinking of like all the different kinds of grandmothers in the world. Because really, it's like innumerable. I don't really have anything other than I guess I also saw that I guess you could say that NaN has kind of reached enlightenment, right? Because it's one with everything, except JavaScript, which doesn't count. All right. But one other quick aside, I just want to mention because when you first said NaN is a number, I was like, yes. Because I've been a very strong proponent of that concept for quite some time. So much so that I actually made a T-shirt. This is a shameless plug. If you go to symphonysubconscious.com, you can buy a NaN is a number T-shirt, and you should, because I'm really broke. Yeah, that part wasn't a joke, but you should. I mean, just check it out. I think I did a good job with it. It's symphonysubconscious.com. NaN is a number. And you would look like such a nerd, and you would do Lewis proud. He would really appreciate it. I will send you one too, so just send me your contact information. I will send you a shirt. Anyway.